Good evening everyone, I am Mr. Ish. Our video today is this, trigonometry, the study of circles. And there's a bit of a sarcasm involved over here, or a bit of an exclamation. All along when you're studying trigonometry, especially in high school, we learned that trigonometry is basically the study of triangles and the related angles that come via means of those triangles. But it's interesting to think about trigonometry also as being study of circles, because the trigonometric aspects are very well defined in terms of circles, or you can very well define circles in terms of trigonometry. And you can do so very easily by thinking about the concept of the unit circle, defined in terms of a Cartesian coordinate system having a center here in the origin, and any point on this curve over here can be defined in terms of a trigonometric aspect. Think about it. If you draw any point over here, and we'll call this point P, point P will represent a coordinate x comma y, and you can define this in terms of trigonometry. We're talking about here the unit circles. If you classify this line over here, the distance of this line, you can call it r. You can bring this down right over here, make a right triangle. Of course, everything here is stemming from this unit circle. You have a little angle over here, we can call that theta, and then you have something called an x and a y. We know this point P, which lies on this unit circle, a certain radius away or segment away from the origin or the center at a certain angle with reference to your reference horizontal. You can look at everything here in terms of trigonometry. The value of x in terms of cosine theta is equal to x over r. R here is representing a hypotenuse of this triangle, and the value of y, sine theta, is equal to y over r. You solve individually. X is equal to r cosine theta, y is equal to r sine theta, and suddenly this point P we're looking at can be defined in terms of this, r cosine theta and r sine theta, all based here on the inherent relationship between trigonometry and circles. So yes, indeed, trigonometry can be viewed as one of the disciplines that enables you to study circles, but not the only discipline, because it also has a big thing with regards to triangles. Let's look over here at this thing over here, P, r cosine theta, r sine theta. If the radius over here of this unit circle, we can say x squared plus y squared. If this radius of this unit circle is a 1, these r values become 1 here. In this case, the point P can be defined easily by cosine theta, sine theta. Why? Because the coefficient of 1 is meaningless, because if there's no coefficient, it's always understood to be a 1. This here represents an x value, this here represents a y value of this coordinate here. If you look at these points on a unit circle having a radius of 1, you can say this is 1 comma 0, this right here is 0 comma 1, this is minus 1 comma 0, and here this point will be 0 comma minus 1. And then this is why you can develop these shortcuts. Cosine of 0 is always equal to 1. Why? Because you're looking at the x value. Sine of 0 is always equal to 0, because here you're looking at the y value of this coordinate. How about this? Sine of 90 is always equal to 1, because you're looking here at the y value. Cosine of 90 is equal to 0. Likewise, you can do the tangent of that. Cosine of pi is always equal to minus 1. Why? Because you're looking here at this point. Minus pi would land you right over here. Sine of 3 pi over 2, which is 270, is always equal to minus 1, because here you're looking at the y value. Then by just these basic reference points, you can develop the values for sine, cosine, tangent, secant, cosecant, cotangent, all because we are talking here about a unit circle having a radius of 1, for which you develop these reference points. And from these 4 reference points, you can get the values of all the 6 trigonometric functions for each of those reference points. Another very interesting phenomenon that arises just from this unit circle and the relationship between trigonometry and that unit circle is this. If you know by means of the Pythagorean identity, x squared plus y squared is equal to r squared, you know this right here represents the value of x, this represents the value of y. You can plug these values here, the x and the y coordinate of this point P. You have r cosine theta all squared, and then you have r sine theta all squared is equal to r squared. You have r squared cosine squared theta plus r squared sine squared theta is equal to r squared. Here you can very well isolate the r squared. You have cosine squared theta plus sine squared theta is equal to r squared. You can cancel out these r squares by taking everything on the other side, and then you get the very important Pythagorean identity, sine squared theta or sine squared x plus cosine squared theta or cosine square x is equal to 1. And you get the very major fundamental trigonometric identity established just by means of the relationship between trigonometry and circles. Obviously, if you have a unit circle over here which has a radius of 1, you know you're looking at this this point over here with a radius of 1. You know this right here is a cosine theta for this point, and then sine theta, and then very easily you arrive at the same identity because here the radius happens to be 1. You can just look at everything over here as sine square theta plus cosine square theta is equal to 1 square, which is just a 1. This right here is my y value being squared. This right here is my x value being squared is equal to r square. So if you have a clear relationship or value for an r, you can very easily arrive at a single step. Another important concept that brings trigonometry and circles together is the concept of arc lengths. If you start with an x and a y axis, you can draw a little point over here and then do a proper rotation of your marker or your tool and draw another point over here and connect these at a certain angle, whatever that angle might be. You can draw a curved line and you've developed a sector over here. You know, the sector, which represents a portion of your hole, has a certain radius, it has an angle, and it has a certain arc length, which is from here to right over here. If an interesting fact is this, you know this point over here represents point P, which is cosine theta comma sine theta, which we've already shown you at the beginning, right over at this point. If r is equal to 1, we're talking about a unit circle with a radius 1, you know the formula for a arc length is always s is equal to r theta. If r is equal to 1, then your arc length becomes the value of your theta but in radians. If supposedly theta was 60 degrees, you wouldn't say my arc length is 60 degrees. You have to express theta 60 degrees in radians, and you know that would be pi over 3. Now you can say my arc length is equal to pi over 3 because this value over here can be used as a length value in addition to a angle value but in radians. We're talking about pi over 3 rads. That happens to be my arc length over here. If we're looking here at theta of 60 degrees, this point P right over here, what would it be? The point P would be cosine pi over 3 comma sine pi over 3. And you know we're talking about here x and a y value. Cosine of pi over 3 is what? 1 over 2. Sine of pi over 3 using trigonometric ratio is root 3 over 2. By means of that very interesting trigonometric identity which I've already talked about, sine square theta plus cosine square theta is always equal to 1. Here we're looking at always equal to 1. You can do cosine square theta plus sine square theta should give you that 1. Here's my cosine value, 1 over 2 square, right, plus root 3 over 2 squared, and you should get a 1, and indeed you do. 1 over 4 plus 3 over 4 is equal to 4 over 4, which is equal to 1. So you do get this good relationship play out over here. You just don't have to make that confusing mistake that your theta in degrees is representing your arc length when arc length here is usually measured in radians, which is why if you do a arc length of 2 pi, you're essentially gone in a complete circle, and this is exactly why cosine of 0 is equal to 1, because you have that very important 1 comma 0 point on the unit circle, and also why cosine of 360 is also equal to 1, simply because cosine 0 and cosine 360 happen to fall on the same point. Additionally, if you have a representation such as this, you're essentially showing a sector which has a certain arc length defined in terms of the radius and an angle. If again this angle happens to be 60 degrees, or let's just say pi over 3, we know we've already talked about this point to be 1 over 2 comma root 3 over 2. We've already established that. If you were to draw this point down a line going into the x-axis, you know you've created a right triangle. This value over here will be 1 over 2 comma 0, and if you were to draw this across, you know this value here would be 0 comma root 3 over 2. If someone were to ask you what is the area which is created here in terms of this additional area which is outside the triangle but which is very well in the sector, because you know when you're looking at a sector you're creating this little curved line, but if you try to draw a right triangle you end up having this additional area between the height of this triangle and then the outer arc length of that sector. What would be the area of that sector? You can do so by doing the total area, which would be the total area here of the sector, right? Total area is the sector area, and then you do the sector area of the sector minus area of the triangle would give you that leftover area, which is what we're looking at right over here. How could you determine the area of this triangle given the coordinates we have? Well, we know we have an x-axis dimension over here and we have a y-axis dimension. The x-axis happens to be the length of the segment from origin to 1 over 2 comma 0. The x-axis dimension happens to be 1 over 2. The y-axis dimension happens to be from here, or you can just say from origin up to this. And the y value here would be root 3 over 2. And you know what the area of a triangle, it's base height over 2. That's the area of a triangle. And you plug in these values, you have 1 over 2 times root 3 over 2 all over 2. You have root 3 over 4 over 2. You have root 3 over 8. That's the area of the triangle. But what's the area of the sector? The area of the sector is always half r squared theta. And theta here we're measuring and expressing in terms of radians, root 3 pi over 3. So what's the area of the sector? It's half times the radius, which is 1 square, times theta pi over 3. So the area of the sector ends up being pi over 6. So what's this leftover area? It's the area of the sector minus root 3 over 8. And you could do this in terms of a convenient answer with a common denominator 24. 6 goes to 24 4 times. 4 pi minus 3 root 3, and that would be the area of this shaded portion right over here. And very well, you can calculate this shaded area here in terms of calculus. So let's do that. What we'll do is we'll write this answer right over here on the top, and then we can compare it to the answer we obtained from integral calculus procedure, 4 pi minus 3 root 3 over 24. And you can of course get a numerical value over here. Let's do that. Numerical value 0.3071. 0.3071. I've just transferred everything from this side to that side, made it a little more large. You know, we're continuing that same question from the previous slide where we had something which looked like this arc, and we were examining the area of this region. You know, this point over here was 1 over 2 comma root 3 over 2. We had a radius here of 1, and we were looking at the examination of that leftover area. We did this example over here by means of geometry. The total area of the sector minus the area of this triangle gave us this area in between. But we have to do this by means of integral calculus. You'd be surprised if you were to put these points in. You know exactly this right here is 1 over 2 comma 0, and this right here in terms of height is 0 comma root 3 over 2. This is just me basing this everything on x and y value, and it's right. And we know the radius is 1. So if from here to here is a length of 1/2, and then from here all the way to here must be a total distance of 1, because the radius is 1. This right here is the radius of 1. This right here is the radius of 1. Don't look at this image to scale, because it isn't. From here to here, the triangle represents, when you're drawing it down, half of this segment right over here, which is the radius. It doesn't look like that based on the picture, but it is. Because if you were to properly draw a 60-degree angle with regards to a sector, 60 degrees would be much closer here to the vertical axis. You'd have 30 here, 60 here. Now if you draw the proper arc and you draw this down here, now you actually have like 1 over half here and 1 over half here. This right here is a half segment. This from here to here is a 1 segment. So don't look everything on face value, because things are never drawn to scale. Anyhow, we have to look at the examination of this leftover area using integral calculus, and there are about 2 ways of doing this. Using the properties of integrals, you can do it by 2 ways, and I know I'm presenting you items here which are beyond our comfort level or techniques we've talked about, but that's fine, because in these preliminary videos we're showing you what is the extent you can do with the material you're about to learn in these upcoming weeks. You can look at everything over here in one of 2 ways. Way number 1, let's just call this way number 1. You know your intervals. If you know this is 0, this right here is half, and this right here is 1, because I've shown you that. You can look at everything as the area of the sector minus area of the triangle will give you area of the leftover, and you could word it out this way. The area of the leftover part we're looking at, I will just call that area question mark, would be equal to area of the sector, because it's the sector minus the triangle, and the sector happens to have an interval from 0 to 1, and you'd have the sector formula over here, the sector area with regards to dx, and then from there you'd minus the area of the triangle, which happens to have an interval from 0 to 1 over 2, and you'd have the triangle formula over here with regards to dx. And you know, I've talked a little bit about this, whether we're looking at yt minus yb, top boundary curve minus bottom boundary curve, or we're looking at in terms of xr minus xl, right side versus left side. These are what would come in over here. Anyhow, You can look at it in this way: 1 over 0, 1 to 0 to half to 0 would then give you this leftover portion, which would be the area of this, would give you the area of the leftover portion, and that leftover portion I'm still calling as a question mark, but it would have the interval from 1 over 2 to 1. Remember, this is a property of integral, and I can refer you back to my properties of integral video where I've shown you how you can define these intervals. This right here is the harder way of doing it. The benefit of calculus is you can jump directly to the area of examination, which is right over here. Clearly see the interval. The area which we're looking for, this question mark, is clearly from 1 over 2 to 1, and you can get the formula of this curve over here, which we would just call f of x and dx, and that's it. This would be our formula we would use to directly calculate the area of this versus doing this elaborate procedure. I'm going to go for this right over here. Though we can do it in both ways, this will be longer, much longer. This will be much quicker, and we have to do this. And we're going to do everything over here with yt minus yb. Why not? Even though here we have a right side and left side curve, the right side curve would be the curve of this arc. The left side would be this vertical line, x is equal to 1 over 2. We can do that. But this will prove out to be easier because in a way you do have a top curve and a bottom curve. This curve serves as a top curve, and this x-axis serves as the bottom curve. So let's look at this in terms of this way. Our equation must be in the y equals format. Right, y equals format, and we must integrate with respect to dx. All we have to do is determine yt and yb, and it's easy. Our top boundary curve is this arc, but if you were to extend this arc all the way around, what are you actually having and seeing? You're seeing an equation of a circle, which was x squared plus y squared is equal to r squared, and therefore y was equal to square root of r squared minus x squared, but we already know what r was. So our equation was y is equal to 1 minus x squared. 1 minus x squared, and we already see the interval here, half to 1, from 1 over 2 to 1. And we have the function already set. That's my yt. Here's my yt. What's my yb? The yb is this x-axis, which is what y equals 0, which is meaningless. Y equals 0 is nothing. So this is the only equation which you'll come right into this entire integration, which is why this scheme number 2 is so much easier. Scheme number 1 is so much more difficult. We'll finish this question right here with this scheme number 2. I'll play it all out for you and we should get exactly that answer. So let's take this integral calculation for this area right here to completion, the area of this. And I've already given you the preliminary information. Our area for this leftover portion, which I'm just calling as a question mark, is going to go from 1 over 2 up to 1. And I've already told you yt and yb is just going to be y top, because this right here bottom x-axis is meaningless. It's square root of 1 minus x squared with regards to dx. And you see a trigonometric function will arise out of here. With practice, time and experience, you'll start seeing trigonometric functions come. When you see something like this, you have to start thinking about trigonometric substitution techniques. But here, nothing will zero out like as it was in the previous derivation video. So we won't be doing that shortcut technique over here. If a is equal to 1, x is equal to sine theta, dx is equal to cosine theta, theta 1 and theta 2, because when you do substitution, these intervals change. Everything will get plugged into here in terms of x, and you'll solve for theta. Sine theta is equal to half, theta is equal to inverse sine of half, which is what, pi over 6. Sine theta is equal to 1, theta is equal to inverse sine of 1, which is pi over 2. Remember, you'll learn all of this. We're just building interest over here by showing you all of this. This becomes pi over 6, pi over 2. You end up having over here, we'll do some quick steps over here. We'll have 1 minus sine squared theta, and here dx was cosine theta d theta. Let's not forget that. Cosine theta d theta. By means of substitution or isolation and simplification, you'll have square root of cosine squared theta over here, and you still have this cosine theta, all of this. This becomes cosine theta, this becomes cosine theta, you multiply them together, you get cosine squared theta in all of this part. It becomes cosine squared theta d theta. But cosine squared theta by means of the power reducing formula can be split into 1 plus cosine 2 theta over 2 d theta. By means of the properties of integrals, you can separate everything over here around this positive sign, and let's do it. You'll have pi over 2, pi over 6. This 1 over 2 can be brought out as a coefficient. You will learn these techniques. Here's my plus sign right over here. And this other 1 over 2, which is attached to the cosine 2 theta along with its own interval and the same interval for right now, cosine 2 theta d theta. The integral of this right here is nothing more than just a theta. and we have an over 2 sitting over here over the interval pi over 2 and pi over 6. When you do a polynomial substitution technique, because this is a composite, u is equal to 2 theta, du is equal to 2 d theta, and you solve for d theta, you bring the 2 down as a denominator, and you will see all of this come into play when you learn this technique. You'll have 1 over 4, you'll have the integral of cosine u, which will be a sine u, which we have to learn in the future. These things will change by means of the polynomial substitution technique. This will become pi over 3, this will become pi. Now you have to integrate, meaning direct integration procedures. You will do the upper limit, the lower limit in place of theta. You do pi over 2 minus pi over 6, which is pi over 3. Here you get pi over 3 all over 2. Here let's bring the 4 down over here. You have sine of 180 minus sine of 60. Sine of 180 is 0. But sine of 60 using trigonometric ratios will be sine of pi, which is 0, minus that sine of 60, which is minus root 3 over 2. Remember, sine of 60 is root 3 over 2, but by means of direct integration, a minus comes into the picture. So this is what you get over here from all of this procedure right here. But we can simplify this and we'll do it right here. We have a pi over 6 coming over here. Pi over 3 divided by 2 is a pi over 6. Minus root 3 over 2 is the same thing as bringing this 2 denominator down right over here. You get minus root 3 over 8. And you can see what this pi over 6 minus root 3 over 8, pi over 6 minus root 3 over 8 simplifies to the same thing, and you get in terms of the denominator the same answer, 0.30709. The integral calculus derived procedure, area for this portion right here, the area in that small region between the sector, outer periphery, between the arc length and the triangle which falls in between. So that's the area right here, and we did it by using the short procedure by doing direct area evaluation for the interval from here to here versus doing from 0 up to 1 and minusing from that 0 up to half to get the leftover. That more convoluted procedure can be done, but it's more difficult. Directly examining this procedure in terms of yt or y minus yb or even xr, because this right here is an xr and xl, it can be done, but in that case you'll be doing derivation, integration in terms of dy, and you'd have to change your equations into x equals formula. You see this arc right over here, this would again come from this formula right here, x squared plus y squared equals r squared in that scheme, but in that scheme you'd solve for x. That would be your x, or your right side curve. It would be x is equal to square root of 1 minus y squared. That would be your xr equation. What would be your xl? It will be this x equals 1 over 2. xl here would be x is equal to 1 over 2. But you see how you have an extra equation coming into the way? It would make things a little difficult. And your interval, it would be from, we would look along the y-axis. You know you're going here from a 0 in terms of the y-axis, and then you'd be looking up over here up to root 3 over 2 in terms of the new lower limit and the new upper limit. So our interval would be 0 comma root 3 over 2. But let me just make some space right over here. For interest's sake, we can just create the equation form of this integration procedure. We won't carry it through, but you can just see how it would have been in terms of appearance. You'd be looking at area of that left orb. It would be exactly this, from 0 up to root 3 over 2. You would be looking at xr minus xl. xr we've already established to be square root of 1 minus y squared. xl we've established to be 1 over 2, which is my vertical line, x equals 1 over 2 right over here with respect to dy. You would have a little bit more complexity here involved only simply because of this extra part over here, and you know you'll end up having 3 integrals or 3 pieces come out. This would be piece number 1, and you'd have 2 pieces come from right over here, especially when the cosine squared theta comes in and you split it up over 1 plus cosine 2 theta over 2, and you split it across this positive sign, so you'd have 3 integrals. One would be this 1 over 2, the other would be cosine 2 theta over 2, and then you know this one right here is the third integral. And you'd have this one having the interval from 0 to root 3 over 2, but this one would have those trigonometric radian intervals from 0 up to pi over 3, and then by means of this polynomial substitution, this second part over here will have from 0 up to 2 pi over 3. So you'd have a set of intervals come through. One would be from 0 to pi over 3 for this first part, 1 over 2 d theta. For the second part, plus cosine 2 theta over 2, when you do the substitution for that polynomial, you'd have 0 comma 2 pi over 3. And then of course for this you're still having 0 comma root 3 over 2 for the interval. So you see This procedure was rather easy because you only ended up having two. Here you'd have three, 1, 2, and 3. Three separate integrals all arise from right over here. Two of which would come out from this trigonometric aspect, and the third one is right over here. Anyhow, the answer would still come out to be the same, and you could always try that out at a future date when you learn and are comfortable with all of this. The purpose of this video was just to really discuss the inherent relationship between trigonometry and circles and how calculus at a higher level can be the binding glue between those two. And that's all I wanted to show you in this video. I hope you enjoyed this video. Thank you for watching. Have a nice day.